So in this example, we want to answer the following question. What would the muzzle velocity of the noisy cricket be if instead of involving some advanced alien technology, as it obviously did, if instead it fired bullets of mass 20 grams and the shooter was thrown backwards at 10 meters per second? So to solve this problem, we want to be able to conserve momentum. The bullet, gun, Will Smith character, these are all objects interacting with each other, so we should be able to conserve momentum and figure out what the muzzle velocity of the noisy cricket would be if it was just a conventional gun. So when you're doing this kind of problem, it's very helpful to first draw a before and after picture of the either collision or, in this case, explosion. So for the before picture, everything is together. So we have Will Smith's character here with the noisy cricket and the bullet inside the gun. And everything is at rest. All velocities are equal to 0. After the noisy cricket fires, then we have Will Smith's character with the noisy cricket, and he is being flung backwards at some velocity, which we've defined here to be 10 meters per second. And then the bullet is flying forward with some velocity equal to the muzzle velocity of the noisy cricket. So there's our before and our after picture. So next, what we need to do is we need to conserve momentum. So we need to write down a conservation of momentum expression. So we can say, since our system is basically the bullet and Will Smith, we can say that the mass of the bullet times the velocity of the bullet initial, so that's the initial momentum of the bullet, plus the mass of Will Smith times the initial velocity of Will Smith, or we could switch those subscripts around too if we wanted, but this is the initial velocity of Will Smith, so his initial momentum, that's equal to the mass of the bullet times the velocity of the bullet final plus the mass of Will Smith times the final velocity of Will Smith. So some of these things we know are equal to 0. Everything in the beginning is at rest. Everything is 0, so all of the momentum in the beginning scenario are equal to 0. So that simplifies our expression quite a bit. So 0 then is equal to the mass of the bullet, velocity of the bullet final, plus the mass of Will Smith times the velocity of Will Smith final. So what we want to find is the final velocity of the bullet. And we know the mass of the bullet. We know the velocity of the shooter after the gun is fired. But what is the mass of Will Smith? Well, fortunately, the internet knows all things, including Will Smith's weight around the time this movie was filmed. And according to these interwebs, Will Smith's weight was 210 pounds. So we need to then convert that into eventually into kilograms, but this is a weight, so since it's a weight, we need to first convert it into newtons, since newtons is the SI unit for weight. So let's see, 1 pound is equal to 4.448 newtons. So Will Smith weighs 934 newtons, but since this is a weight we know is equal to mg, and mg in this case is 934 newtons. So therefore the mass of Will Smith is equivalent to 934 newtons divided by 9.8. meters per second squared, which gives us a mass of 95.3 kilograms. Okay, so now we have all of the quantities involved in our problem, so we can solve for the velocity of the bullet final. So first, what we'll do is move this term to the other side. And so let's see, the mass of the bullet times the velocity of the bullet final is going to be equal to minus the mass of Will Smith times his final velocity after the gun is fired. And then we can divide both sides by the mass of the bullet. So plugging in numbers, the final velocity of the bullet is going to be equal to minus Will Smith's mass, which we found to be 95.3 kilograms. And his final velocity after firing the gun was 10 meters per second. And according to our diagram, that 10 meters per second is occurring in the negative direction. So I'll put in a minus 10 meters per second. And then the mass of the bullet is 20 grams or 0.02 kilograms. So that gives us a bullet velocity of 4.77 times 10 to the 4 meters per second. And that seems rather large, and in fact, if we convert 4.77 times 10 to the 4 meters per second into miles per hour, we'll find that it's over 100,000 miles per hour, which isn't really physically realistic for any gun, which indicates, of course, that this was some advanced alien technology that he was using. So next, let's look at this question. A boy is standing on one end of a floating raft that's stationary relative to the shore, and he walks to the opposite end of the raft, away from the shore. So as a consequence, what happens to the raft?